In the silent void of space, where stars are born and galaxies collide, lies a mystery that has captivated humanity since we first gazed upward. How did life begin? Not just any life, but the intricate, self-replicating, evolving tapestry of organisms that transformed a barren rock into the vibrant blue jewel we call home. For billions of years, Earth was a molten wasteland, bombarded by asteroids and scorched by solar radiation. A place where the very concept of life seemed impossible. And yet, against all odds, something extraordinary happened. From inanimate matter emerged the first living cells, setting in motion a chain of events that would eventually produce forests, oceans teeming with life, and conscious beings capable of pondering their own origins. This is the story of one of science's greatest puzzles, the moment when chemistry became biology. It's a tale that spans cosmic timescales, connects the smallest molecules to the grandest planetary processes, and forces us to reconsider what life truly means. Today, we stand on the precipice of revolutionary discoveries that could finally reveal how non-living matter crossed the threshold into living systems, potentially rewriting our understanding of biology and our place in the universe. Our journey begins approximately 4.6 billion years ago, when our solar system was nothing more than a swirling cloud of gas and dust, a molecular nebula left behind by the death throes of ancient stars. Within this cosmic nursery, gravity began its slow, inevitable work, pulling particles together into increasingly dense clumps. At the center, temperatures and pressures rose until nuclear fusion ignited, giving birth to our sun. Around this newborn star, the remaining material began to coalesce into planets through a process called accretion. Earth formed during this chaotic period, growing from countless collisions between planetesimals, small rocky bodies orbiting the young sun. These violent impacts released tremendous energy, keeping the early Earth in a molten state for millions of years. Imagine a world without oceans, without continents, without even a solid crust. A glowing sphere of liquid rock, its surface temperature exceeding 2,000 degrees Celsius. This was the Hadean Aeon, named after Hades, the Greek god of the underworld, and for good reason. The Earth was a hellish landscape, constantly reshaped by asteroid bombardments that would have vaporized any attempt at stability. During this period, known as the Late Heavy Bombardment, Earth was pummeled by debris left over from planetary formation. Some of these impacts were cataclysmic, like the one that likely created our moon when a Mars-sized object called Theia collided with the proto-Earth. This impact was so violent that it melted the entire planet, creating a global magma ocean. The debris from this collision eventually coalesced into our celestial companion, which would later play a crucial role in stabilizing Earth's axial tilt and creating tidal forces that may have contributed to the emergence of life. As the bombardment subsided, Earth began to cool. The surface solidified into a thin crust, while volcanic activity released vast quantities of gases, water vapor, carbon dioxide, nitrogen, and smaller amounts of methane, ammonia, and hydrogen sulfide. This outgassing created Earth's first atmosphere, radically different from today's oxygen-rich air. Without the protective ozone layer that would come much later, the surface was bathed in intense ultraviolet radiation from the young sun, which was actually fainter than it is today, but emitted more high-energy particles. Then came the rains, torrential, unceasing rains that lasted for thousands of years. As the planet cooled further, water vapor in the atmosphere condensed and fell to the surface. This wasn't gentle rain, but violent storms that would make even the most severe hurricanes today seem mild by comparison. The water collected in low-lying areas, gradually forming Earth's first oceans. These primordial seas were nothing like today's oceans. They were hot, acidic, and rich in dissolved minerals from the newly formed crust. Some scientists estimate that these early oceans may have reached temperatures of 80 to 100 degrees Celsius, creating a global hot soup where the chemistry of life could begin. The formation of these oceans was critical to the origin of life. Water is not just a passive solvent. It actively participates in the chemical reactions that form the basis of biology. Its unique properties, high heat capacity, ability to dissolve many substances, and capacity to form hydrogen bonds, make it essential for life as we know it. Without liquid water, the complex chemistry required for life simply couldn't occur at the necessary scale and speed. But how did this lifeless mixture of rocks, water, and gases transform into the first living organisms? For decades, the dominant theory has been the primordial soup hypothesis proposed independently by Alexander Oparin and Haldane in the 1920s. They suggested that Earth's early atmosphere, composed primarily of methane, ammonia, hydrogen, and water vapor, provided the perfect conditions for organic molecules to form spontaneously. In this reducing atmosphere, energy from lightning, volcanic activity, and ultraviolet radiation could drive chemical reactions that created increasingly complex organic compounds. This theory received dramatic support in 1953 when Stanley Miller and Miller-Urey conducted their famous experiment at the University of Chicago. They recreated what they believed to be early Earth conditions in a sealed apparatus. Water, representing the ocean, methane, ammonia, and hydrogen, representing the atmosphere, and electrodes to simulate lightning. After just 1 week, they found that amino acids, the building blocks of proteins, had formed in the apparatus. This groundbreaking experiment demonstrated that the basic components of life could arise spontaneously from simple inorganic compounds under plausible early Earth conditions. However, modern research has complicated this picture. We now know that Earth's early atmosphere likely contained less methane and ammonia and more carbon dioxide and nitrogen than Miller and Urey assumed. When scientists repeat the experiment with these more realistic atmospheric compositions, fewer organic molecules form. This has led researchers to explore alternative environments where life's building blocks might have assembled. One promising candidate is hydrothermal vents on the ocean floor, particularly alkaline hydrothermal vents like those found at the Lost City Field in the Atlantic Ocean. These vents release warm, mineral-rich water through porous rock structures that create microscopic compartments resembling cells. The temperature gradient between the hot vent water and the cold ocean creates natural proton gradients similar to those used by living cells to generate energy. The mineral walls of these vents contain iron and sulfur compounds that can catalyze the formation of organic molecules and even facilitate simple metabolic reactions. Another possibility is that life began in tidal pools or on clay surfaces. Clay minerals have a layered structure that can concentrate organic molecules and provide templates for their organization. Some clays even have catalytic properties that accelerate the formation of RNA molecules, a crucial step in the origin of life. The wet-dry cycles of tidal pools could have driven the polymerization of nucleotides into RNA strands, as drying concentrates molecules and facilitates bonding, while re-wetting allows for further reactions. Perhaps most intriguing is the role of deep-sea hydrothermal vents in providing both the energy and chemical disequilibrium necessary for life's emergence. At these vents, mineral chimneys create networks of microscopic pores that act as natural compartments. The temperature difference between the hot vent water, around 70 to 90 degrees Celsius, and the cold ocean, 2 degrees Celsius, creates thermal gradients that could have driven early metabolic processes. Crucially, the alkaline fluid from these vents reacting with the acidic ocean water creates natural proton gradients, a fundamental energy source that all living cells use today through a process called chemiosmosis. But having building blocks isn't enough. Life requires information, the ability to store instructions for replication and metabolism. This is where RNA enters the picture. The RNA World hypothesis suggests that RNA, which can both store genetic information and catalyze chemical reactions, was the first self-replicating molecule. Unlike DNA, which requires complex machinery to replicate, RNA can sometimes copy itself with minimal assistance. Laboratory experiments have shown that under certain conditions, RNA nucleotides can spontaneously form chains, and some RNA molecules can catalyze their own replication. The transition from RNA-based life to the DNA-protein world we know today represents another critical step. DNA is more stable than RNA for long-term information storage, while proteins are more versatile catalysts than RNA. This division of labor, DNA for information, proteins for function, likely evolved gradually, with RNA serving as the intermediary between the two. The emergence of the genetic code, which translates nucleotide sequences into amino acid sequences, remains one of the most mysterious aspects of life's origin. Another crucial development was the formation of membranes. Without a barrier separating the internal chemistry from the external environment, life's delicate chemical processes couldn't be maintained. Fatty acids and other simple lipids can spontaneously form vesicles in water, spherical structures with a double-layered membrane similar to modern cell membranes. These protocells could have encapsulated RNA and other molecules, creating the first cellular compartments. Remarkably, when these vesicles grow by incorporating more lipids, they could divide spontaneously, providing a simple mechanism for early reproduction. The fossil record provides tantalizing clues about when life actually emerged. The oldest widely accepted fossils are stromatolites, layered structures formed by microbial mats from 3.5 billion years ago in Western Australia. But even older evidence comes from isotopic signatures in rocks from Greenland dating back 3.7 billion years. These rocks show a carbon isotope ratio that suggests biological activity, pushing the origin of life back to within a few hundred million years after Earth's surface became habitable. This rapid emergence of life has profound implications. If life appeared quickly under Earth's early conditions, it suggests that the transition from chemistry to biology might be a relatively common process in the universe. The window between Earth becoming habitable, around 4.4 billion years ago, when oceans formed, and the earliest evidence of life, 3.7 to 4.1 billion years ago, may have been as short as 300 million years, a geological blink of an eye. Yet another theory challenges the notion that life originated on Earth at all. The concept of Panspermia proposes that life, or at least its building blocks, arrive from space. Meteorites like the Murchison meteorite, which fell in Australia in 1969, have been found to contain amino acids and other organic compounds. Comets and asteroids could have delivered these prebiotic molecules to early Earth during the late heavy bombardment. Some scientists even suggest that fully formed microbial life could survive the journey through space protected within rocks, potentially seeding Earth with life from elsewhere in the cosmos. Laboratory experiments have shown that certain microorganisms, particularly extremophiles, can survive conditions similar to those of space travel: extreme cold, vacuum, and radiation. Tardigrades, for example, have survived exposure to the vacuum of space during experiments on the International Space Station. While this doesn't prove that life originated elsewhere, it demonstrates that the transfer of life between planets is theoretically possible. A more radical version of panspermia, sometimes called directed panspermia, speculates that an advanced civilization might have intentionally seeded Earth with life. While this idea captures the imagination, it lacks scientific evidence and merely pushes the question of life's origin to another location without solving the fundamental problem. The search for life's origins has also led scientists to reconsider what life actually is. Rather than viewing life as a sudden event, some researchers propose that it emerged through a series of incremental steps, with properties we associate with life appearing gradually. Metabolism might have come first, with self-sustaining chemical networks forming in hydrothermal vents. Information storage could have developed later, followed by compartmentalization. This continuum perspective suggests that the boundary between non-life and life may be blurrier than we once thought. Modern research is increasingly focusing on systems chemistry, studying how networks of chemical reactions can become self-sustaining and self-replicating. Scientists have created chemical systems that exhibit lifelike properties. They maintain themselves far from equilibrium, respond to environmental changes, and even undergo a form of evolution. These chemical ecosystems provide valuable models for how life might have emerged from non-living matter. One particularly promising area of research involves autocatalytic sets, networks of molecules where each molecule is produced catalytically by other molecules in the set. Such systems can grow, maintain themselves, and even undergo selection, exhibiting key properties of living systems without the complexity of modern biology. In 2023, researchers demonstrated an autocatalytic set that could evolve in response to environmental changes, representing a significant step toward understanding how chemical systems might transition into biological ones. The discovery of extremophiles, organisms that thrive in conditions once thought inhospitable to life, has dramatically expanded our conception of where life can exist. Microbes have been found in boiling hot springs, acidic rivers deep underground, and even within nuclear reactors. These discoveries suggest that life is far more resilient and adaptable than previously imagined, increasing the potential locations where life might have originated on early Earth. Deep within Earth's crust, scientists have discovered entire ecosystems living independently of sunlight, powered by chemical energy from the planet's interior. These subsurface biospheres, extending kilometers below the surface, may represent environments similar to those where life first emerged. The discovery of microbial life in such extreme environments has profound implications for the search for extraterrestrial life, suggesting that habitable zones around stars might be much broader than previously thought. Advances in analytical techniques are allowing scientists to probe ever deeper into life's origins. Sophisticated mass spectrometry can detect trace organic molecules in ancient rocks, while computational models simulate the complex chemistry that might have occurred on early Earth. The development of synthetic biology has enabled researchers to construct minimal cells with only the essential components for life, providing insights into what the earliest living systems might have looked like. One of the most exciting frontiers is the search for alternative biochemistries. All known life on Earth shares the same fundamental biochemistry: DNA for information storage, RNA for information transfer, proteins for function, and lipids for membranes. But could life exist with different molecular foundations? Scientists are exploring the possibility of life based on different solvents, like methane instead of water, alternative genetic materials, or even silicon-based chemistry. While such life would be radically different from Earth life, Its discovery would revolutionize our understanding of biology. The James Webb Space Telescope is now searching for biosignatures in the atmospheres of exoplanets, gases that might indicate biological activity. Simultaneously, missions to Mars and icy moons like Europa and Enceladus are looking for evidence of past or present life in our own solar system. These efforts are informed by our growing understanding of life's origins on Earth, creating a feedback loop between astrobiology and origins research. Perhaps the most profound implication of understanding life's origins is what it tells us about life's inevitability. If the transition from chemistry to biology is a natural outcome of planetary evolution under certain conditions, then life may be widespread throughout the universe. The laws of physics and chemistry appear to be universal, suggesting that wherever conditions are right, the same processes that led to life on Earth could occur elsewhere. This perspective transforms our understanding of humanity's place in the cosmos. We are not merely accidental visitors in a lifeless universe, but the product of natural processes that may be unfolding across countless worlds. The atoms that make up our bodies were forged in the hearts of stars, and the chemistry that sustains us connects us to the fundamental processes of the universe. As we continue to unravel the mystery of life's origins, we're not just learning about Earth's past. We're gaining insights that could help us recognize life elsewhere, engineer novel biological systems, and even create life in a laboratory. Each discovery brings us closer to answering one of humanity's oldest questions. Are we alone in the universe? The journey to understand life's origins is far from complete. Many questions remain unanswered. How did the genetic code emerge? What drove the transition from RNA to DNA and proteins? How did the first cells develop the complex machinery for energy production and replication? But with each passing year, new discoveries bring us closer to solving this cosmic puzzle. In laboratories around the world, scientists are recreating early Earth conditions, synthesizing novel forms of life, and probing the chemical pathways that might have led to biology. Space missions are searching for evidence of life beyond Earth, while advanced telescopes scan distant worlds for signs of biological activity. The convergence of these efforts may soon provide answers that have eluded humanity for millennia. What's certain is that understanding how life began on Earth will transform our understanding of biology, reshape our search for extraterrestrial life, and perhaps even redefine what it means to be alive. As we stand on the threshold of potentially revolutionary discoveries, we're reminded that we are not separate from the universe. We are the universe becoming conscious of itself, seeking to understand its own origins. This quest to uncover life's beginnings is more than just an academic exercise. It's a fundamental part of the human story. By understanding how life emerged from non-life, we gain perspective on our own existence and our responsibility as stewards of this fragile biosphere. The same processes that gave rise to the first living cells continue to sustain the incredible diversity of life on Earth today, a testament to the power and resilience of biology. As we continue to explore this profound mystery, one thing becomes increasingly clear. Life is not a miraculous accident, but a natural expression of the universe's inherent tendency toward complexity and organization. From the swirling clouds of stellar nurseries to the intricate dance of molecules within a single cell, the same physical laws guide the emergence of order from chaos. In this grand cosmic story, the origin of life on Earth is not an isolated event, but a chapter in the ongoing narrative of a universe that continually creates and evolves. The question is no longer whether life can emerge from non-life, but rather how commonly and through what pathways this transformation occurs. With each new discovery, we move closer to understanding our place in a living universe, one where the spark of life may be waiting to ignite on countless worlds across the cosmos.